All right, so get this. What if I told you there's this mathematical swindle that can, like, seemingly prove 1 equals 0? Crazy, right? Today, we're going deep on the Eilenberg Mazur Swindle. It's a concept that kind of twists logic and plays with infinity.
Yeah, it's a bit like a magic trick, you know? Like
Yeah.
the Eilenberg Mazur Swindle uses these like seemingly legit steps to get to this totally absurd conclusion.
Yeah, exactly. And it all starts with these infinite sums. Imagine slicing a pizza into like infinitely thin slices. You just keep going and going forever,
Mm.
right? An infinite sum is kind of like trying to add up the areas of all those tiny, tiny pieces, but like our brains are used to finite things.
Right, yeah, exactly. And infinite sums, they don't really behave the same way as finite sums, you know? Like in a finite sum, you get to an answer, but with an infinite sum, it just never ends.
It's wild. So how does this swindle actually work?
Well, imagine like you have an equation with an infinite sum on one side, and the swindle basically involves like removing a term from that infinite sum and then rearranging the other terms.
So it's like you're sneaking a slice off your infinite pizza
Yeah.
and then rearranging all the rest so it looks like nothing's missing.
Exactly. But here's the thing. By like carefully choosing which terms to remove and how to rearrange the rest, you can make it look like something totally impossible. Like 0 equals 1 is true.
Well, that's trippy. But it doesn't actually prove that 0 equals 1, right? It just shows how our brains kind of mess up when we think about infinity.
Yeah, yeah, that's a good way to put it. It shows the limits of our finite intuition when we try to deal with these infinite processes.
Right. Okay. So let's get specific. One of the classic examples of this swindle involves something called the infinite direct sum of groups. I know that sounds kind of scary, but bear with me. A group is basically like a set of elements with a specific operation that follows certain rules. Like, think of a group of apples. You can combine them, but you still have a group of apples.
Right. And a direct sum is just a way of like combining multiple groups into a larger one, like adding oranges to your apple group to get a fruit group. But in this case, we're talking about an infinite number of groups.
Whoa, infinite groups of fruit. That's a lot of fruit. So how does the swindle work with these groups?
So the Eilenberg Mazur Swindle uses this infinite direct sum to like prove something that's totally counterintuitive, which is that you can have a bunch of these non-trivial groups, meaning like groups that have more than one element, and they can somehow be equivalent to the trivial group, which only has one element.
Okay, so it's saying a basket overflowing with fruit is the same as a basket with one grape.
Exactly. And the way they do this is by using something called an isomorphism, which is basically a way of mapping one group onto another while preserving the structure.
So like finding a perfect mirror image, but in a different form.
Exactly. So the swindle, it constructs this isomorphism in a way that like seemingly collapses this infinite direct sum down to the trivial group. It's like taking an infinitely long train of numbers and somehow squeezing it all down to a single point.
Wait, but how is that even possible? Doesn't that break like the rules of how groups work?
Well, that's the trick, right? The swindle, it exploits this infinite nature of the direct sum to create this isomorphism that's not really valid for all elements. In simpler terms, like the mapping breaks down at certain points. It's kind of like, a magician's sleight of hand. It works as long as you don't look too closely.
So it's not actually a real proof, but it's like a demonstration of how our assumptions about finite processes, they can mislead us when we're dealing with infinite structures.
Yeah, exactly.
Okay. So we've seen how the swindle works with these groups, but it doesn't just stop there, right?
Right. This mathematical magic trick has a few more tricks up its sleeve. It also applies to things like rings and manifolds.
Rings and manifolds. Okay, I'm intrigued. Tell me more.
All right. Well, a ring is basically a set of elements with two operations, addition and multiplication. Think of like a clock face where adding hours wraps around. That's a simplified way to think about a ring.
Okay, I think I get it. So how does the swindle work with these rings?
So in the world of rings, the Eilenberg Mazur Swindle can actually create a proof that 1 equals 0.
Wait, hold on. 1 equals 0 in a ring. That's even crazier than the infinite groups thing.
Yeah, it is. Imagine like adding one apple to a basket being the same as adding no apples at all.
It just doesn't make sense.
Just
How is that even possible?
Well, it's the same kind of manipulation of infinite processes. Basically, by manipulating an infinite series of elements within the ring, the swindle forces the series to converge on both 1 and 0 at the same time. It's like a mathematical illusion where the rabbit both appears and disappears at the same time.
Whoa. Okay, and what about manifolds? What are those?
All right. Manifolds, they're a little more complex, but we can break it down. Think of a manifold as a surface that can be like curved and twisted, but at any given point it looks flat, like the surface of a sphere.
So like locally it looks flat, even though the overall shape is curved.
Yeah, exactly. And the Eilenberg Mazur Swindle can be used to create a proof that an infinite dimensional manifold, a space with infinite dimensions, is homeomorphic to a single point, a space with zero dimensions.
Homeomorphic. I think that's a word I need to look up.
Yeah, it's a bit of a mouthful, but it basically means that two spaces are topologically equivalent. Like imagine a donut and a coffee cup.
Right.
You can mold one into the other without tearing or gluing anything. That's homeomorphism.
Oh, okay. So it's saying that you can take this infinitely complex multidimensional space and you can like squish it down into a single point.
Yeah, in a way, yeah. It's another illusion created by the swindle. Basically, it constructs a transformation that appears to collapse this infinite dimensional manifold down to a single point. But this transformation, it's not really well defined for all points. It breaks down when you try to apply it universally.
So it's another example of how the swindle exploits infinity to create these paradoxical results, right?
Exactly. It really forces us to confront the limits of our intuition, and it highlights the need for really rigorous definitions when we're dealing with infinity.
This Eilenberg Mazur swindle, it's like a mathematical chameleon or something.
It is.
But it's more than just a bunch of mind-bending tricks, right? There's a deeper meaning to all of this.
Absolutely. The Eilenberg Mazur Swindle, it's not really about breaking math. It's more about illuminating the hidden complexities of infinity, and revealing these potential pitfalls when we apply finite logic to the infinite realm.
Yeah, yeah. So it's more like a warning sign than a cheat sheet.
Precisely. It's a powerful reminder that even in the world of math, which seems so precise, there are always, deeper layers to uncover and subtle traps to avoid, especially when we're venturing into the infinite.
This has been quite the journey already, and we've only just scratched the surface of this Eilenberg Mazur swindle. But I'm already seeing how this seemingly paradoxical concept, it can actually like help us understand math and the world around us
Yeah,
better.
yeah, and we're just getting started. There's so much more to unravel from the historical context of the swindle to its real world applications. So stay tuned. This deep dive is about to get even more intriguing. Remember that infinite pizza we were slicing up earlier? Well, imagine trying to like divide it up between an infinite number of friends. It's the kind of problem mathematicians were struggling with back in the early 20th century, and it led to some crazy discoveries about infinity.
So we're going from like swindling with equations to
Mhm.
like really wrestling with infinity itself. This is getting deep.
It is. It is. You see, for a long time, mathematicians, they relied on these kind of intuitive notions of sets and infinity, but as they started to like explore these concepts more rigorously, they ran into all these paradoxes and inconsistencies that kind of shook the foundations of what they thought they understood.
It's like finding out the ground you're standing on is actually quicksand.
Yeah.
And all because we started asking like deeper questions about infinity.
Exactly. And one of the key players in this whole mathematical earthquake was Georg Cantor. He was a German mathematician who really revolutionized how we understand infinity. And his work actually ties directly into the challenges that the Eilenberg Mazur swindle kind of exposed.
Yeah, I've heard of Cantor's work, with like different sizes of infinity, but it's always seemed like so abstract and well, infinite.
It is mind-boggling. Cantor introduced this concept of transfinite numbers, which are numbers that represent different sizes of infinity, and he showed that there's actually like infinitely many different infinities, each one bigger than the last.
Hold on, infinity. So it's not just that things can go on forever, but there are different levels of forever.
Exactly. Cantor proved that like the set of all natural numbers, 1, 2, 3, and so on, that's infinite. But the set of all real numbers, which includes, decimals and fractions, that's actually a bigger infinity. It's like there are different levels of forever.
Okay, my brain is officially melting. But how does this all connect back to the Eilenberg Mazur swindle? It feels like we've jumped from a magic trick to like a philosophy lecture.
They are connected, though. The swindle shows us how our intuition about these finite processes can break down when we try to apply them to infinity. Cantor's work, on the other hand, shows us that infinity itself is way more complex than we might think.
So the swindle is like a warning sign,
Mm.
right? Like be careful when you're dealing with infinity. And Cantor's work is like a map showing us just how big and complicated that landscape really is.
Yeah, that's a great analogy. Both the Swindle and Camcor's discoveries, they came from a time of intense mathematical, scrutiny. They forced mathematicians to confront the limits of their assumptions and to develop like more rigorous methods for handling these really complex concepts.
It's amazing to me how something as seemingly simple as forever, can lead to such big questions and revolutions in how we understand things. It's like looking up in the night sky and realizing that what we see is just a tiny fraction of what's actually out there.
Exactly. The Eilenberg Mazur Swindle, it's like this mischievous guide, right? It points out all the potential pitfalls and paradoxes that pop up when we try to apply like finite logic to the infinite. It's a reminder that the rules we take for granted can totally break down when we step outside the boundaries of our everyday experience.
So the swindle isn't just a clever trick. It's a tool for understanding the foundations of math and the very nature of infinity itself. But if we can prove something as crazy as 1 = 0 using this swindle, does that mean math is like broken or inconsistent?
Well, that's a question that's puzzled, philosophers and mathematicians for ages. The Eilenberg Mazur Swindle doesn't necessarily mean that math is broken, but it does show how important axioms and definitions are in shaping our mathematical systems.
Axioms and definitions.
Yeah.
Those sound a bit like the building blocks of any logical system.
Yeah. Exactly. Axioms are those basic assumptions that we start with, the givens, we accept them without proof. And definitions, they give us like the precise meanings for the terms that we're using. The Eilenberg Mazur Swindle shows us that even a small change in our axioms or definitions can lead to totally different conclusions.
So it's like a game where the rules can be changed to create totally different
Yeah.
results, right?
Yeah.
It makes you wonder about what truth really means in math. Is it absolute or is it relative to the framework we're using?
That's a really deep question, and it's one that the Eilenberg Mazur Swindle really makes us think about. It suggests that math, while it's incredibly powerful, it's not like this one absolute truth. It's more like a system of reasoning that's built on this carefully chosen set of axioms and
This
definitions.
is this is making me rethink my whole idea of what math is. It's not just about like formulas and calculations.
Yeah.
It's about exploring the very limits of logic and reason.
And it's always evolving. The Eilenberg Mazur Swindle, it's a product of a time when math was developing rapidly, and it still sparks new insights and debates even today.
So it's not just a historical thing. It's a living concept that keeps challenging our assumptions and pushing the boundaries of mathematical thought.
Precisely. And as we dig deeper into its implications, we'll see how it connects to fields beyond just pure math from physics to computer
This
science.
is all this is all so fascinating, but I got to admit my brain is starting to feel a little fried from all this talk about infinity and paradoxes.
Mhm.
Is there any way to make this discussion a little more concrete? Something I can grasp without getting lost in the abstract.
Absolutely. The great thing about math is that it often connects to the real world in unexpected ways, even when we're dealing with abstract concepts like infinity. Let's explore some of those connections and make this swindle a little more tangible.
Perfect. I'm ready to see how this dance of numbers plays out in the real world.
Okay. Well, let's start with a field where the strange and the counterintuitive are basically the norm. Quantum mechanics.
Quantum mechanics. Now that's a world where things get even weirder than infinite sums. I've heard about particles being in two places at once and cats being both dead and alive.
Yeah, you're not wrong. Quantum mechanics is notoriously mind-bending, but it's also incredibly fascinating. And there are some really interesting parallels between the Eilenberg Mazur Swindle and certain phenomena in quantum mechanics.
Okay, I'm definitely intrigued. Tell me more.
Okay, so in quantum mechanics, particles can exist in multiple states at the same time. It's like a coin that's both heads and tails at the same time until you actually look at it. This is called superposition.
Right. I've heard of that. It's
Yeah.
it's one of the things that makes quantum mechanics so hard to wrap your head around.
Exactly. And this principle of superposition, it has some pretty wild implications. For example, it allows for the possibility of quantum entanglement, which is where two particles become linked in a way that their fates are intertwined, even if they're like physically separated by huge distances.
So it's like two coins that are flipped at the same time, and they always land on the same side, even if they're miles apart.
Precisely. And what's fascinating is that this entanglement phenomenon, it can be described mathematically using concepts that are similar to the ones used in the Eilenberg Mazur Swindle.
Wait, so you're saying that this mathematical swindle that can make 1 = 0 can also help us understand this spooky action at a distance that Einstein was so puzzled by.
In a way, yeah, both the swindle and quantum entanglement, they highlight how important it is to consider the relationships between different parts of a system, even if they seem like infinitely far apart or logically incompatible.
That's mind-blowing.
Yeah.
It's like these concepts are challenging our very ideas of space and time and causality.
Exactly. And they demonstrate this amazing connection between these seemingly separate fields of knowledge.
This is incredible, but my brain is definitely in need of a recharge after all this mind-bending exploration.
Yeah.
It's amazing how a deep dive into a mathematical concept can lead to such profound questions about the nature of reality itself.
And we're not done yet. There's still more to uncover, from the practical applications of the swindle in computer science to its broader philosophical implications. So
Yeah.
buckle up, because this deep dive is about to take us even further down the rabbit hole.
All right, so we've gone through this bizarre world of infinite sums tangled with paradoxes and even like dipped our toes into quantum mechanics. But before we wrap up our deep dive into this Eilenberg Mazur Swindle, I'm curious about something. You mentioned earlier that this mathematical flight of hand has like practical applications, especially in computer science. How does a concept that seems so abstract and theoretical connect to the world of coding and algorithms?
It's a great question, and it really all boils down to data structures. These are the fundamental building blocks of any computer program. Think of, arrays, lists, trees, all the ways that we organize and store data in a computer's memory.
Right, data structures. They're like the digital filing cabinets that keep everything organized.
Yeah.
But how does infinity fit into all of this?
hmm
I mean, my computer definitely doesn't have infinite memory.
That's true for physical memory, but conceptually, a lot of programs have to deal with data streams that could potentially be infinite. Imagine like processing an endless stream of social media posts, or simulating a physical system over an unlimited time period.
Ah, okay, I see. So even though the computer's memory is finite, the the programs that we write often have to deal with this concept of infinity.
Exactly. And that's where the Eilenberg Mazur Swindle, it becomes surprisingly relevant. It reminds programmers that the rules and assumptions that work perfectly fine for finite data structures, they might not hold true when you're dealing with ones that are potentially infinite.
So it's kind of like a cautionary tale for coders, like a reminder that infinity can really mess things up, even in the most carefully crafted algorithms.
Precisely. The swindle highlights the importance of designing algorithms and data structures that can gracefully handle these nuances of infinity without causing unexpected errors or crashes. It's a bit like, trying to fit an infinite number of books onto a finite bookshelf. You need a really clever strategy to avoid a total collapse.
That's a great analogy. It,
Yeah.
it makes me wonder if there are any real world examples of where this kind of thinking has actually prevented problems in computer science.
Absolutely. One area where this awareness of infinity is really crucial is in the design of operating systems. Operating systems manage all the resources of a computer, and they often have to deal with processes or loops that could potentially be infinite.
So if a program gets stuck in an infinite loop, that's where things can freeze up or crash.
Exactly, but by incorporating safeguards and techniques that are mindful of the potential pitfalls of infinity, operating systems can gracefully handle these situations and prevent system-wide failures.
That's amazing. It's like having a safety net for infinity, preventing those infinite loops from sending everything spiraling out of control.
Yeah, it's a testament to how a seemingly abstract concept like the Eilenberg Mazur Swindle can have a very real impact on the technology that we use every single day.
Okay, so the swindle has implications for coding and operating systems, but you also mentioned like broader philosophical questions. What kind of philosophical rabbit holes does this swindle open up?
It really forces us to confront some really fundamental questions about the nature of knowledge and truth and the limits of our understanding.
Yeah, and we've seen how the swindle can prove things that are obviously false, like 1 = 0. Does this mean that math is inherently flawed or inconsistent?
That's a question that people have been debating for centuries. The Eilenberg Mazur Swindle, it doesn't necessarily mean that math is broken. Instead, it highlights the really crucial role of axioms and definitions in shaping our mathematical systems.
Axioms and definitions, those like the ground rules and the dictionary of any mathematical system, right?
Exactly. Axioms are those basic assumptions that we accept without proof. They're the starting point from which we build our entire system. And definitions, they provide these precise meanings for the terms we use, making sure that we're all speaking the same mathematical language.
But the swindle shows us that even tiny changes to these axioms or definitions can lead to totally different conclusions. It's like playing the game where the rules can be changed to create totally different outcomes.
Precisely. The Eilenberg Mazur Swindle, it reminds us that mathematics, while incredibly powerful and consistent within its own framework, it's not this monolithic absolute truth. It's a system of reasoning that's built on this carefully chosen set of axioms and definitions.
So it's more about understanding the assumptions and the framework that we're working within rather than searching for some ultimate absolute mathematical truth.
Exactly. It's about recognizing the inherent limitations of any system of logic and the crucial role of human ingenuity and creativity in shaping our understanding of the world.
This whole deep dive has been an incredible journey and honestly a bit of a mind-bending roller coaster ride. We started with this mathematical swindle and we ended up exploring the very nature of infinity, the quirks of quantum mechanics and the philosophical foundations of mathematics itself. What's the key takeaway here? What's the one big idea you hope listeners will take away from this exploration?
I think the most important lesson is that the Eilenberg Mazur Swindle, despite its name, it isn't about deception. It's about illumination. It sheds light on these subtle complexities of infinity. It challenges our assumptions, and ultimately it deepens our appreciation for the power and the limitations of mathematical reasoning. It's a reminder that even in the most rigorous and logical of fields, there's always more to learn, more to question, and more to discover.
It's like the swindle is this mischievous guide leading us through this labyrinth of mathematical thought, revealing these hidden pathways and unexpected connections along the way.
Exactly. And through this exploration, we gain a richer and more nuanced understanding of not just mathematics, but of the universe itself. After all, mathematics is the language that we use to describe and understand the cosmos. And the Eidenberg Mazur Swindle, it reminds us that this language, like the universe itself, is full of surprises and wonders waiting to be uncovered.
Thank you so much for taking us on this incredible deep dive. It's been a truly eye-opening and mind-expanding experience.
The pleasure was all mine. Remember, the Eilenberg Mazur Swindle reminds us that there's always more to learn, more to explore, and more to marvel at in the world of mathematics. So keep questioning, keep exploring, and keep that sense of wonder alive.